Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the 15th numerical on sampling theorem. Please note, this is one of the previously asked MSc question. Let me read out the question first. A 1 kHz signal is flat top sampled at a rate of 1800 samples per second. And the samples are applied to an ideal rectangular low pass filter with a cutoff frequency of 1100 Hz. What frequency components are available at the output of the low pass filter? Let us start with the solution part. It is given that a 1 kHz signal is flat top sampled. Therefore, the frequency of the signal is represented as Fm equals 1 kHz. Further, we are told the signal is sampled at a rate of 1800 samples per second. Therefore, the sampling frequency is 1.8 kHz. In this video, I am going to use a different approach than the one that I have been previously using. That is, previously when such a question was asked, we were drawing the spectrum of the input signal and then we were applying the equation for the spectrum of the sampled signal, and then by finding the new frequencies, we would draw the spectrum of the sampled signal. However, in this particular numerical, as I said, I will use a different approach. From the sampling theorem, we know that the spectrum of the sampled signal will exhibit replicas of the original signal spectra, where the original spectral lobe is shifted left and right by a value of n Fs. Let me write it down here. In this numerical, we are going to use this concept and we will then find the new frequency values for every value of n. We will first write that the frequency components of the sampled signal are given by Fm plus or minus NFS and minus Fm plus or minus NFS, which I will write now. Now, having identified the frequency components of the sampled signal, let us now substitute values for n ranging from 0, 1, 2, etc. and find the new frequency components. For example, for n is equal to 0, this part will become Fm plus or minus 0 and this will be minus Fm plus or minus 0. We are told Fm is equal to 1 kHz. So, this is 1 kHz and this is minus 1 kHz. Therefore, the frequency components are plus 1 kHz and minus 1 kHz. Let us now move on and find the same for n is equals to 1. For n is equals to 1, the first frequency component is Fm plus or minus 1 Fs and this will be minus Fm plus or minus 1 Fs. So, this will be 1 plus or minus 1 into Fs is given as 1.8 and this is minus 1 plus or minus 1 into 1.8. Now, note that there is a plus or minus symbol involved. So, every calculation will give two frequency components. First, I will take the plus symbol. So, 1 plus 1.8 will be 2.8 kHz and 1 minus 1.8 is minus 0.8 kHz. Coming to the second frequency component, here we have minus 1 plus 1.8. So, it will be plus 800 Hz or plus 0.8 kHz and minus 1 minus 1.8 is minus 2.8 kilohertz. Similarly, let me calculate for n is equals to 2. In this fashion, you can continue for more values of n and find new values for frequencies. However, for this numerical, these computations are sufficient enough. Let us come back to the numerical and see that the cutoff frequency of the ideal rectangular low pass filter is given as 1.1 kilohertz. I'll write it down here. Right. Since we are asked to find the frequencies that appear at the output of this rectangular ideal low pass filter, we simply identify those frequency components of the sample signal which are either less than or equal to the cutoff frequency of the ideal rectangular filter. Right. Now, having said that, let us now go back and check all the computations and identify the frequencies either less than or equal to 1.1 kilohertz. By analyzing the computations, we find only 4 frequency components that appear at the output. They are plus or minus 800 Hz and plus or minus 1 kilohertz. So, the frequencies that appear at the output of the LPF are plus or minus 800 Hz and plus or minus 1 kilohertz. Right, that is the final answer for this numerical. Well, that's about this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.